My name is Sibaji, Assistant Professor of Mathematics, Durgapur Government College. Today's topic, set in R. Outline of my presentation: neighborhood, open set, limit point and isolated point, closed set, adherent point, and reference. First we define interval. Let A and B belongs to R and A less than B. Then the subset X belongs to real number R, A less than X less than B is said to be an open interval. We see that A and B between all elements in R is said to be interval, and A and B, these two elements not belongs to this set. The subset X belongs to R, A less equal to X less equal to B. This set is called closed interval. In this set, A and B, both elements in this set. The subset X belongs to R, A less than X less equal to B, and the set X belongs to R, A less than X less equal to X and less than B are said to be half open or half closed interval. This half open interval and denoted by open A close B and close A open B respectively, where both the end point of the interval belongs to R. The interval is said to be bounded interval because A and B belongs to R and this is a finite number. So these interval are a bounded interval. Therefore, the given all interval are bounded intervals. Now we define unbounded interval. We see that the subset X belongs to R, X greater equal to A, where A is a real number. This set is an infinite open set. We see that X belongs to R, X greater equal to X is an infinite closed set. This is denoted by close A and infinity. The subset X belongs to R, X less than A is an infinite open interval. And same as thus X belongs to R, X less equal to A, where A is a real number. This is closed interval, but these four intervals are unbounded interval, and this interval is denoted by A infinity, close A infinity, minus infinity A, minus infinity A are all are unbounded interval. If A equal to B, then the closed interval is a singleton set. This is singleton set defined here. Now we define neighborhood. What is neighborhood? Let X belongs to R, a subset of R is said to be neighborhood of C if there exists an open interval AB such that C belongs to AB, subset of S. A closed bounded interval containing a point C may not be a neighborhood of C. For example, 1 and 2, this is not interval of 1 because no open interval containing 1 subset of 1 3 closed interval. So this is not a neighborhood of K 1. Let C belongs to R. The union of infinite number of neighborhood of C is also neighborhood of C. This is a result. Another result is the intersection of finite number of neighborhood of a point C is a neighborhood of C, but the intersection of infinite number of neighborhood of C may not be a neighborhood of C. For example, we choose minus 1 by n to 1 by n open interval. This is a neighborhood of T 0 for all n. This is the collection of neighborhood of 0. But we see that intersection n equal to 1 to infinity open interval minus 1 by n to 1 by n open interval equal to 0 is a singleton set. This is not a neighborhood of 0. Next we define interior point. Let S be a subset of R. A point x in S is said to be interior point of S if there exists a neighborhood in X of X such that in X is a subset of S. The set of all interior point is said to be interior of S, and this is denoted by int S. Some example of interior point. If we take a set S equal to 1, 1 by 2, 1 by 3, then the interior of X is 5 because there is no interior point. S has no interior point. Next we choose n S equal to n, the set of all natural number. Then int S is 5 because the natural number set not contain interior point. If we choose the set S equal to rational number, set of rational number Q, then int S is 5 because there is no interior point in Q. If we choose S equal to open interval 1, 3, then whole interval is interior S because all point of this set is an interior point of this set. Let we choose S equal to R. Every point of S is an interior point of S. So interior of S is R. If S equal to 5 is null set, then no interior point, so therefore int S equal to 5. Now we define open set. Let S be a subset of R. S is said to be open set if each point of S is an interior point of S. Example of open set, or verify this set are open or not. We see that S S equal to 1, 1 by 2, 1 by 3. So S is not an open set because this set has no interior point. If we choose S equal to n, then S is not open set because natural number n has no interior point. If we choose S equal to Q, set of all rational number, then S is not open set because Q has no interior point. If we choose open interval of 1, 3, then int of S equal to S. So S is an open set. If we choose S equal to R, every point of S is an interior point of S. So int of S equal to R, so S is an open set. If S equal to 5, null set, then S has no interior point. So S is an open set. So null set is an open set. Now we give some important result. If S be a subset of R, then S is open set if and only if S equal to interior S. Previous example we see that if S equal to interior S, then this set is open set. This is another definition of open set. Many books refer this definition. The union of finite number of open set is always open set. The intersection of finite number of open set in R are open set. The union of arbitrary collection of open set in R is an open set. The intersection of infinite number of open set may not be open. In previous example of neighborhood, we choose minus 1 by n 1 by n open interval. These open interval are open set for all n, but the intersection of this open set is only 0 singleton set, which is not open. This is the example, counter example of infinite intersection of open set in R may not be open set or not necessarily open set. Or another two result are S be a subset of R, then S is an open set. Interior of S is an open set, and interior of S is the largest open set containing S. Content S. Next, limit point. Let S be a subset of R. A point P in R is said to be limit point of S if every neighborhood of P contains a point of S other than P. Let S be a subset of R, then the set of all limit point of S is said to be the derived set of S, and it is denoted by S dash. The famous theorem, Bolzano-Weierstrass theorem, it says that every bounded infinite subset of R has at least one limit point. Example of derived set. If we choose S equal to 1, 1 by 2, 1 by 3, then the derived set of S equal to only 0. Let S equal to n, set of natural number, then the derived set is 5. If we choose S equal to Q is a set of rational number, then S dash is R. If you choose the open interval of 1, 3, then the derived set is closed interval of 1, 3. Every point of S is a limit point of S in R. So derived set of R is R. If we choose S equal to 5, then S has a no limit point, so derived set of S equal to 5. Now we define isolated point. Let S be a subset of R. A point X in S is said to be isolated point if X is not limit point. Therefore, X is an isolated point of X if for some positive epsilon there exists a neighborhood nx epsilon contain no point of X S other than X. X ছাড়া কোনো point S এর মধ্যে থাকবে না. For example of isolated point, if we choose S equal to 1, 1 by 2, 1 by 3, dot dot dot, this set, all point, every point of this set is an isolated point. Natural number set n, every point of n is an isolated point. We see that in Q, in previous example, all derived set of Q are R. So no isolated point in Q. If we choose S equal to 1, 3 open interval, then there is no isolated point. If we choose S equal to R, then S has no isolated point. Next, closed set. Let S be a subset of R. S is said to be closed set if derived set of S subset of S. Here are some example of closed set. Phi is a closed set. R is also closed set. Q is not closed set. S is open interval 1, 3 is not closed set. N, natural number n is closed set because there is no limit point, so derived set is a subset of S. And the first example, S equal to 1 half 1 by 3, this limit point is 0 or derived set is singleton 0, so this set is not closed set. Some important result of closed set. Let S be a subset of R, then S is closed set if and only if R minus S is open set. That is, S complement is open set. The union of finite number of closed set of R is closed set. The intersection of finite number of closed set of in R is closed set. The intersection of arbitrary collection of closed set in R a closed set. The union of infinite number of closed set are may not be closed set. For example, if we choose in equal to 1 plus 1 by n, 5 minus 1 by n, then this all in are closed set because all interval are closed interval. But union of n equal to 1 to infinity equal to 1 5 open interval, which is open set, not closed set. So union of infinite number of closed set may not be closed set. Next, adherent point or cluster adherent point. Let S be a subset of R. A point X is said to be adherent point of S if every neighborhood of X containing a point of S. It follows that X is the adherent point of X, then every neighborhood of X intersection S not equal to 5 for every epsilon greater than 0. The set of all adherent point is said to be closure of S, and it is denoted by S bar. Some important result, if we choose S subset of R, then S bar equal to S union S dash being in the derived set. S subset of R, then S is in closed set if and only if S equal to S bar. Let S be a subset of R, then S dash is closed set and it is the smallest closed set containing S. S bar is the intersection of all closed superset of S. There is no non-empty proper subset of R is both open and closed in R. Now we define dense set and perfect set. Let S be a subset of R. A subset T, subset of S is said to be dense in S if S subset of derived set of T or T dash. In particular, S is said to be dense set in R or dense or everywhere dense if every point of R is a limit point of S, or equivalently S dash equal to R. Let S be a subset of R. S is said to be dense in itself if S subset of S dash. Let S be a subset of R. S is said to be perfect set if S is dense in itself and closed. That is, if S summon S dash, S equal to S dash. Some example. The set of rational number Q is dense in R since Q dash equal to R. Let S equal to open interval of 1 2, then S is a subset of S dash, so S is dense in itself. The set of rational number dense in itself because Q subset of Q dash equal to R. The set of R is dense in itself. Let S equal to close interval of 1 3, then S is a perfect set. Next, reference some books. Thank you all.